this computer. And yeah, we're officially being recorded. Okay, so hello everyone to the first lunch and learn of 2023. Woohoo! Today we have our one and only Luke Williams, and he's going to present on GD&T, which is like an essential skill if you want to make drafting, um, design. What is it? Make drafts that make sense to a machinist. Okay, without
Yep.
further ado, yeah, Luke, take it away.
All right. Excellent. So yeah, just as something you said, GD&T is really important for making drafts and making it understandable to machinists. And so the first thing that I want to point out is that there are a lot of great resources for GD&T, and I wanted to point out the textbook that I'm using for this session, which is one that I found on the library at online. And so we're just going to be going through a couple chapters of this, kind of doing a brief overview of GD&T because it is a whole textbook worth of information. We're not going to get through that whole thing, but hopefully we'll get the foundation down. Right. So obviously the first thing you need to know when you're doing GD&T is obviously dimensioning and tolerancing. That's sort of the bread and butter of any technical drawing. And so the first thing I want to show you is chapter 2.5, where we talk about linear tolerances. And so linear tolerancing is divided into two types. The first is limit tolerancing, and the second is plus minus tolerancing. Limit tolerancing, the highest and lowest value for a dimension is placed. This is sort of a direct way of saying these are the upper and lower limits. And you don't have what is essentially called a nominal, which is like the center. Instead, you just sort of have the boundaries. So obviously, then we also have plus minus tolerancing, and we can see an example in this table 2.2. So if you look at number one here, we've got the nominal, which is the center of the dimension, which is 0.25 inches. And we have a plus tolerance and a minus tolerance. So the plus tolerance in this case is 0, which is sometimes useful for saying that you don't want to have any extra material. And then you have a minus of 5 thousandths. What is also important from this table is the difference between the norms for inch tolerances and millimeter tolerances. There are a couple of differences here. The first I may notice is that with inch tolerances, we add zeros to the end of the decimal so that we match up with the precision of the tolerances that we have. So for example, with a 1/4 inch here, instead of saying 0.25, we say 0.250 to match up with that tolerance of 0.005. So that's sort of like almost a significant figure kind of deal. It just goes to make sure that we are specific as to the precision that we're dealing with here. This is mostly an American thing, and you'll notice that with the millimeter tolerances, we don't have this. For millimeter tolerances, we have instead whole numbers do not have a decimal point, and they do not have any trailing zeros at the end of it. Now, this obviously is a more non-American, or you might say everywhere else except for America kind of deal. And so that's just kind of useful to know and review if you're trying to make any drawings that are going to Germany or something like that. So just a couple little differences there. Not hugely important for us, but interesting and maybe useful in the future to be aware of. Okay, so that's basically the main thing with dimensioning and tolerancing for linear dimensions. I do want to move on to angular dimensions, which is 2.7 here. So I know as engineers, we're very used to working with radians, and that's, what our calculator is always accustomed to. However, when it comes to drawings, we're always going to be using some form of degrees. And that's going to be either degrees with decimal points, or decimal parts, I should say, or we're going to be using degrees with minutes and seconds. And this is because all of the machine tools that machinists and manufacturers around the world use, they are all in degrees, because radians is just a much more difficult thing to work with with your hands, if you think about it. So obviously, degrees with decimal parts is pretty simple. If you're unfamiliar with degrees, minutes, and seconds, I'll explain that real quick. So obviously, we have 360 degrees in a circle. But if you want to split a degree up into minutes, essentially 1 degree is equivalent to 60 minutes, quite similar to time in that respect. And so that's just sort of a subdivision, a way of subdividing a degree into 60 minutes. And if you need more precision than that, you can subdivide, once again, a minute into seconds. And once again, that is a conversion of 60. So 1 minute is 60 degree seconds. And so that's essentially the two different ways we can describe an angular dimension in our technical drawings. So one is not necessarily better than the other. It is mostly preference. As you will find out, a lot of things are based on preference when it comes to drafting, and there's a lot of subjective thought going in here. What we try to do, though, is give at least a few rules in GD&T to sort of narrow those subjective parts down. So when we're specifying angular tolerances, we're going to do essentially a very similar thing with linear tolerances. This example is a plus minus tolerance, and you can see that we have both an example of decimal and minutes and seconds in figure 2-3. Nothing really too surprising here, but if you do get confused exactly how you're supposed to draw this, this is a perfect example right here. Okay, so that is pretty much it in terms of just run-of-the-mill dimensioning and tolerancing. So once again, we've got linear dimensions, which is just sort of the length of things, and then we've got angular dimensions, which are the angle of things, and that's pretty much, using those two, we can sort of define any sort of shape that we want. Okay, so with this in mind, though, I wanted to bring up an example that I've drafted up on NX. And that is these two drawings that I've made here. So these two drawings are of the same part. The part is essentially a 2-unit cube with a 1.5 unit cube and a 1 unit cube on the end. And so it's essentially almost like a Christmas tree, if you think about it. But I have 2 different ways that I am dimensioning this part here. So the first way is this one that I'll call series dimensioning, where we dimension each cube individually, right? And so instead of how we do in parallel dimensioning, where we use a single face as sort of the reference for all dimensions, instead for series dimensioning, we put the dimensions in series, hence the name. So you may be thinking, well, what's the difference? You're still defining each dimension. You're still defining the shape with either way. Why would you choose one over the other? Is there any difference at all? In fact, there is a difference, and that mostly has to do with tolerancing. So let's say we have a tolerance that applies to every dimension here of 0.1 unit, right? So let's say that plus or minus 0.1 is the tolerance for each dimension that we have on this drawing. Whether it's series or parallel, that's the tolerance. Now, consider for a second that if we have that tolerance on the series dimension part, if each of these dimensions end up being 0.1 greater than the value listed here, we'll have 2.1, 1.6, and 1.1 being the real part. And that would be in tolerance according to this drawing. However, if you care about the overall length of this part from base to tip, suddenly you're going to have a length that is 0.3 greater than what you technically asked for, if that makes sense. So this concept of tolerances compounding on each other is generally why we use parallel dimensioning instead of series dimensioning, because in this case, we constrain the overall length to 4.5 and put a tolerance on that instead of individual tolerances. And so in this drawing, we will have controlled the overall length of this part to 4.4 and 4.6. While in the series example, we will have a maximum error of 4.8 and a minimum error or a minimum size of 4.2. Now, this is all to say that in general, we might use parallel, but there are situations, however, where we might use series. And so to illustrate that, let me just quickly share with you a whiteboard here. And let's imagine, for example, that instead of having a solid part, we have a circular bulkhead. And on that bulkhead, we have 2 holes for a U-bolt. And so obviously we've got a U-bolt of a specific size, and the distance between these prongs, well, that's going to be fixed, right? So let's say the distance between those 2 prongs is going to be 1 inch, right? Now, if we want to fit this U-bolt into our bulkhead, we're going to need 2 holes. Now, with parallel dimensioning, what we might do is we would take the center of this bulkhead, and we would measure everything relative to that center. However, in this case, what really matters to this bulkhead isn't necessarily the parallel sense of keeping the holes each individually controlled. Instead, what matters to us as a designer for this part, it matters a lot more what the distance between these holes are. That way, we are able to control the tolerance for this 1 inch distance here. So that means that instead of doing it parallel, where we would take a dimension for each, like so, instead, what we would be doing is taking a dimension between each of these features. So the ultimate moral of this is that whether to use series or parallel matters much more on the application of the part you're designing rather than the just a simple rule to pick one or the other. And so you kind of have to think about what exact dimensions matter most for your part. Then you can decide whether you're going to use parallel or series. for your dimensioning scheme. So just a quick review. Parallel is essentially when we use every dimension relative to a common face or a common feature. So in this example, our common feature would be the center. And in our previous example, our common feature would be in the bottom side. Series dimensioning, on the other hand, is dimensioning individual features on their own, presumably because the size of that feature itself matters a lot more than being relative to any other common feature. Okay, so with that, I'll take just a couple seconds here to ask if there are any questions on what we've gone over so far.
I have a question, but I'm gonna ask everyone, like, let everyone and anyone else like ask first. Okay, going once, going twice. Okay, okay.
All
So
right.
my question was, when you're talking about linear tolerances, you mentioned there are two types. There's like plus or minus tolerancing, where there's like a nominal, and then you want a range in between that.
Right.
And there is one where you just have a min and max, and there is no nominal.
That's correct. Yeah.
Um, I guess like why would you pick the first one over? But why would you? Well, I guess like um my question then is like, okay, so when you're actually like making it, machining it, like does that make a difference? Like why do we forego a nominal? Are there cases where that's beneficial?
Sure. So that's a great question. So the first, to answer that, I have to talk about exactly, what is a maximum material condition and I'll skip the jargon. Actually, I'll just sort of explain it. So generally, if you're making a part, unless you're doing 3D printing, generally what you're doing is you're removing material from a piece of stock. So you're taking a cube of aluminum, for example, and you are cutting into that piece of stock to carve out the part within it. And so what that means is the first tolerance that you're going to hit is going to be the larger one for this example. So I'll move over to the parallel example for this. So if we have a big chunk of aluminum and we're cutting it to make this part, and we're getting close to 4.5 as our overall dimension, the first tolerance that we're going to pass is going to be 4.6. So that is going to be what determines when we're going to essentially stop, right? Because you can't really add material on after you've taken it off. So generally what machinists will try to do is that if there is no nominal given, they will go for the upper dimension and kind of be close to that, so they have margin in case they need to cut more material off. And so with the limit dimensioning, generally what you're going to receive in return is a part that is closer to the maximum dimension rather than somewhere in the middle. And that's just to make the job of the machinist easier to hit that tolerance with margin. If we give a nominal dimension, or so a plus minus dimension, I should say with a number in the middle, generally some machinists will still do the same thing where they'll stay near the top dimension, but others might try to go for gold and go for that number that's called out that's in the middle. And so this is kind of, I would say this concept is a little bit more into when you're really getting into really precise tolerancing and you care a lot more whether where they hit on that range. But essentially, that's kind of the difference. It sort of says a little bit different things to the machinist when you do limit dimensioning versus plus minus dimensioning. And generally, if you don't want to have a bad part and just want to get something within tolerance, you will generally use limit dimensioning. But for our purposes, I think it really doesn't matter too much. That's more of an industry kind of concern. And yeah, so I hope that answers your question there. Kind of a long-winded answer, but
No, that was very insightful. Thank you.
okay. Excellent. So that is essentially series and parallel dimensioning there. So what we're going to move on to is sort of the bread and butter of GD&T, really. So while dimensioning and tolerances is sort of the main thing with technical drawings, when it comes to GD&T specifically, we're going to be talking about this little symbol on the right here with the capital A datum. So to talk about that, we're going to have to talk about datums. So what is a datum? Well, if you've never heard of a datum, a datum is a theoretically perfect point, axis, line, plane, or combination thereof that establishes an origin from which all the features of a part can be established. So these can be planes, these can be axes, points, lines, etc. And the role of a datum is to give you a reference, right? So you'll see in figure 4-1, we've got 3 planes here that are going to be a simulation of a datum for a part here, or 3 datum planes for a part, I should say. So the whole deal with datums is that we're using these planes, axes, etc., as a reference for our features, for the part as a whole. And so every single piece of GD&T starts with your reference, essentially. And so that's why datums are pretty important when it comes to this concept. So what you need to do when you're selecting your datums is you need to immobilize the part. You can't have any degrees of freedom when you complete your selection of datums. And so if you think about these 3 planes, these 3 planes immobilize a part. There's a 4.2 here, which demonstrates that. If you line up your part with the 3 datums here, they will completely immobilize the part in translation and rotation, because you can't rotate without coming off the datum. And obviously you can't move without coming off the datum either. So this sort of is the goal of when you're selecting your datums. And sometimes it's better not to have a plane when you're dealing with, say, a cylindrical part. If you're having a cylindrical part, maybe you want to use the center of that as a reference. Or you can use a combination of planes and a face of that cylinder. And essentially, the goal is to, once again, immobilize that part and give it a control. So I mentioned that this was sort of the center of everything in terms of GD&T, and 4-3 sort of illustrates that. For GD&T, what you're going to see a lot is these things called datum features. Now, datum features are symbols that you see on a technical drawing that control a feature, whether it's a hole or a surface or a dimension, etc. And they look sort of like this with two cells here, this cross with a circle. is one example of a symbol that might be in the first cell. Then you've got a tolerance in the second cell. And then trailing that, you've got your datums A, B, and C, which are listed at the end. So this is sort of a general example of a control feature. Essentially, what this particular control feature says is that the first symbol is a location symbol. And so that is calling out the location of a feature on the drawing. And that location is controlled by a 1/100th tolerance, as seen in the second control cell. And then the last three cells, the A, B, and C, those reference the datums that this control is subject to. So, for example, if we were to put this on this part here, you'll see at the top we have that control symbol here. What this is essentially saying is that the location of the hole that it is pointing to is controlled by a 1/100th tolerance. Excuse me. It is controlled by a 1/100th tolerance, and that hole is subject to datum A, B, and C in that order. Right. So what this is saying is that the hole that is shown here is controlled in position, not only in relative to the Z direction, which is where datum A is. It also is controlled in the Y direction, which is where datum B resides, and in the X direction, where datum C resides. And so all three datums there give a control in all three dimensions for this particular hole. So why do all this? Why have this complicated symbol here that shows off the direct location of this hole in such a complicated way? Why couldn't we just use tolerances on these dimensions that we see on the left and right, or the left and bottom of this drawing here? Why couldn't we just use dimensions instead of having this complicated feature here? Well, that mostly has to do with compounding dimension tolerances in quite a similar way as to how we talked about in series dimensioning. So to demonstrate what I mean, I'm going to bring out the whiteboard once again. So imagine we have just a point. Let's say this point is like the center of a hole, and we're trying to control the location of that point relative to two datums. So I'll have this datum on the left. And so once again, this is just a reference plane. And I'll use the symbol for a datum here. And I'll call this symbol, I'll call this datum, datum A. I'll also have a datum on the bottom here, and I'll call this datum B. Okay, so that's our setup. We've got a point, let's just call it point P. And we're trying to control its location relative to A and B. So if we wanted to do, just do dimensions without GD, without the control feature that we saw previously, if we just use dimensions, let's say we have a dimension here relative to B. and that has some value. And then a dimension relative to A, and that has some other value. So naturally, we would have, if we wanted to do this with just tolerances, we would have a plus minus tolerance or a limit tolerance if that's what you wanted. I'll just use plus minus here. And I'll just say I'll have a 1/10 tolerance. And this applies to both X and Y. Okay. So now this fully constrains our point P here. It gives point P limits as to where its location can be using just tolerancing without a control feature like we saw previously. Now, here's the main deal with with just using tolerancing. Consider for a second that we've got our point P floating in space. And let's say this is this dot that I just drew is where point P would be if you were perfect, if you had zero margin, if you machined it perfectly. So you wouldn't need any tolerance, you had a perfect location. Now let's draw a box around here that shows the location that would be within tolerance. So relative to A, we could go plus 0.1. So let's say this line is 0.1 away from the point. And you can go minus 0.1. So you can move, so you have that much room between those two lines to move left and right. That's sort of the box of your tolerance. Similar for relative to B, we've got another two lines, so we can move up 0.1 and we can move down 0.1. And so we've got this whole box of room to put this point based on the tolerances. So plus minus 0.1 in either direction. Now, consider the situation where you have your point, but you have both plus 0.1 and plus 0.1 in the Y and X. So this would bring your point P all the way out to this corner of the box. Now that's technically still in tolerance. However, if you consider how far the point is allowed to move in this direction, it is a lot more than just 0.1. So if you follow me here, under this dimensioning and simple tolerancing of this point P, we constrain this point, but we have situations where we might have this point move all the way to the corner of this box. And if you do a little bit of trig, that's a square root of 2 times the tolerance, which is more than just this tolerance alone. So in this situation, if we move this point all the way to the corner here, it's moved about 14 hundredths away from where it normally would be. Now that's more than 0.1, but still technically this is intolerance. So what we would ideally want, if we wanted to control this uniformly in a sort of circle instead of a box, well, we need a different method of doing this. So this is where our datum control feature comes in. So instead of using a tolerance on each dimension, what we're going to use is our control feature. And now I'm going to sort of haphazardly fill this out. It's not really going to be exactly what it's supposed to look like, but this sort of idea will be there. So we are going to control this location. And this first cell shows the location symbol. And we're going to control this location using a 0.1 tolerance. And then we're going to have a leader line that points to our feature, whether this is a point or a hole or what have you. Now, using this control feature, this allows us to say to the machinist, no, we don't want this. We don't want this box that this point can meander about. Instead, we want to have this circle where the radius of this circle is 0.1, and that is the region that is okay for this feature. So this is a much more specific way of talking about how you want to control your feature within a drawing. It's much more specific because instead of allowing a box, as we see on the top here, instead of allowing this point to meander to the corners of this box and move way out of the way, for example, if this was like a hole, if it moves 0.14, that probably would be too much movement in this design, let's say. We would rather have this hole move less than or equal to 0.1 away from the center. That way we know, as long as it's within that circle, then we know that hole is going to line up with, let's say, a bolt that we're trying to put through it. So this is a much more specific way to control that. So the last couple of things we need for this drawing then is we need to show that these dimensions, X and Y, are subject to this control feature. And the way we do that is we sort of put a box around it like this. And so that says that these dimensions are controlled by this control feature that we placed right here. So that is essentially the main advantage of using GD&T. It makes it a lot more specific as to exactly what tolerance and what your limits are for your drawing. And so this makes it a lot easier for you to fit a hole where you need it to be. And it gives a machinist datums to use to accurately put that feature. And so it's a great way to give a clear communication from designer to manufacturer exactly what you're looking for. And it does it in a way that prevents a compounding of tolerance errors like we have here. So that's sort of the main thing with control features and datums and all things GD&T. So what to take away from this is, while dimensioning may work on its own for most circumstances, there are situations where you might find yourself in a bit of a bind if you allow these tolerances to stack. So if you need a certain level of precision that requires this specific circle or any other kind of tolerancing that you can't quite communicate using just dimensioning and tolerancing, then using control features like this will serve you well. So while we don't have enough time to go through all the kinds of control features and all the kinds of ways that this can be applied, maybe on another day we can go through that kind of thing. But for today, I'll just show you just a few more examples of how this might look using the textbook we have here. So besides using just location, we've also got orientation, profile, form, runout, a whole number of characteristics that we might want to control. And so, as you can see here, we've got a whole list of symbols that we can put into that first cell of our control feature to control any characteristic that we want in our part. Everything from straightness, flatness, to position, concentricity, symmetry, parallelism, angularity, etc. And so this is sort of a list of things you can control using a control feature that you might not be able to using just tolerancing. So that's the main advantage of using GD&T. So hopefully we can get, as we get more advanced in our drafting here at ISS, hopefully we'll get into a little bit more of controlling these kinds of features and characteristics, because it happens all the time in industry. But at the very least, I hope that from this, you might be able to learn how to read drawings that look kind of like this and have these symbols. That way, you can at least get an idea of what the part is looking for in terms of control in its characteristics, and what kind of limits it has in manufacturing. And hopefully that will in turn help you become a better designer with creating your own drawings someday down the line. So that's pretty much everything I have for today. And once again, if you want to learn any more about GD&T, the Illinois Library has a lot of great resources. The textbook I've been using was from a simple search in their database for geometric dimensioning and tolerancing. And so if you want to learn more about how to use these symbols, how to use control features, how to read symbols that you might not know, there are plenty of resources online for you to use as a student, and I highly recommend making use of those resources. So that's pretty much everything, and I'll stick around for any questions you may have. But other than that, that's pretty much it for me.
Okay, thanks so much for the presentation, Luke. Yeah, it was very helpful and information packed and enriching. That's what I could say. Any questions for Luke at this point? Don't be shy. No? Okay, I have like one question. It might be kind of a minor thing. When you were talking about what is it, control features and when you list off the datums that are being used, does the order in which they go matter, or is that kind of like, oh, you just put them in alphabetical order?
Right. So it actually does matter a little bit what order you put them in. The order they put them in is the order of precedence of the datums in that feature. So for example, in this example, it says that it matters more that it's in line with A first, then B, then C.
Okay.
There may be situations where it matters more to have C checked first and then B and C, or B and A. And that's just for example, in this whole, it matters more to have that the depth of the hole first. That's why A is first, I imagine, because it's a through hole. Then it may matter. Then B and C probably matter about equally, so it doesn't really matter exactly what order those are in. But that's the idea of that kind of that order there.
Gotcha. Thank you.
Yeah, absolutely.
Hey, I had a quick question.
Sure.
So for the first control cell that you showed, there are like two methods that you mentioned. One is like the square method, and another is the circular method, which is on the screen right now in the
Mhm.
first control cell. So let's say if I have a control, like my limit is in the 100th position, like 100 decimal. So from the machinist standpoint, which one is a much better one? Like for them, which would be more easier one to consider?
Right. So if you want something easy for the machinist, it would probably be doing just tolerancing without a control feature. And so that would be like what we have with this here, or the first example that I had without the extra symbols, essentially. It will always be easier for a machinist to manufacture something without control features and without precision tolerances. Generally, machinists will charge for material and labor by the hour. And what really drives up labor is precision in tolerancing and any complexity, really. And so while control features are great for putting a specific tolerance on any feature that you need and communicating that precisely, it is difficult and takes more time to manufacture something using that sort of precision, because it's more precise. It takes more time. You need to check it more often. It's really a matter of complexity, the number of controls, and how precise those controls are, that drives up cost and difficulty, I would say.
Okay, got it. Yeah, thanks.
Yeah, absolutely.
Okay, ask your question now or forever hold your peace. Okay, going once, going twice. Okay, I'm gonna pause the recording any minute now. Yeah, thanks so much for presenting, Luke. This was very helpful, and yeah, and thanks for the great questions, everyone. And yeah,